Physics has four mathematically correct answers to the question of what came before the Big Bang. They are mutually incompatible. All four are taken seriously by working physicists. None has been ruled out by experiment. That is the situation. Not a controversy, not a scandal, a situation. And the situation tells you something specific about where physics stands right now, at the edge of what it can reach. The question itself sounds simple. What was there before the beginning? Children ask it. Theologians have answered it for millennia. But when cosmologists ask it, they mean something precise. They mean, what does the mathematics say happened at the moment when the density of the universe becomes infinite in our equations, when the general theory of relativity stops functioning, when the models hit a wall and return nonsense? That moment has a name. Physicists call it the initial singularity. And at the initial singularity, the four answers begin. Before the four answers, one correction. Most people picture the Big Bang as an explosion, a point, a flash, matter flying outward into existing space. That picture is wrong in a specific way. It is wrong about what was expanding. Space itself expanded, not matter moving through space, space. The fabric that contains everything was compressed into a state of extreme density and heat and then expanded. There was no outside for it to expand into. There was no location for the explosion to happen at. The question, where did it explode, has no answer, because space is not a thing that sits inside something larger. This distinction matters for everything that follows, because when you ask what was before the Big Bang, you are asking what was before space and time as we know them. You are not asking about a point in an already existing timeline. You are asking whether there was a timeline at all. Roger Penrose understood this problem early. In the 1960s, he was working at the University of London, trying to prove mathematically that singularities were unavoidable, not just in collapsed stars, but at the origin of the universe itself. He proved it. Working with Stephen Hawking, he showed that under very general conditions, any universe that looks like ours must have begun in a singularity, a mathematical point where density is infinite and our equations stop working. The Penrose-Hawking singularity theorems did not describe what came before. They described a wall. Everything before that wall is, in the language of general relativity, undefined. The four answers are four different ways of approaching that wall. The first answer is loop quantum cosmology, and it was built specifically to remove the wall. General relativity breaks down at the singularity because it treats spacetime as smooth and continuous. Loop quantum cosmology does not. It quantizes spacetime. It treats space itself as made of discrete units, the smallest possible chunks of geometry, each roughly a Planck length across. A Planck length is so small that putting 100 million billion of them end to end would give you approximately the width of a single proton. At that scale, the singularity disappears. Abe Ashtekar was sitting in his office at Pennsylvania State University in 2006 when his team completed the first detailed loop quantum cosmology calculation of the Big Bang. What they found was that when you replace the smooth spacetime of general relativity with the quantized spacetime of loop quantum cosmology, the singularity does not occur. Instead, the universe contracts to an extremely high density, enormous but finite, and then bounces, expands again. What we call the Big Bang is the bounce. Before the bounce, a contracting universe, the same laws running in reverse. This answer has mathematical consistency. The equations are rigorous. Ashtekar's team has continued refining them for 20 years. The model makes predictions about patterns in the cosmic microwave background, the faint radiation left over from the early universe, that are slightly different from standard cosmology. Slightly different and not yet detectable with current instruments. That is where this answer breaks. Loop quantum cosmology makes predictions. The predictions exist. We cannot test them yet. The instruments we would need to see the signature of a pre-bounce universe in the cosmic microwave background are not built. They may never be built. The energy scales involved are so extreme that no accelerator on Earth comes close. The mathematics works. The observational access may not exist. The second answer is the eternal inflation model, and it is built on a mechanism that already exists inside standard cosmology. Inflation is not speculative. Something caused the universe to expand at an extreme rate in the first fraction of a second after the Big Bang, a fraction far smaller than any unit you have a name for. The expansion was so rapid that quantum fluctuations got stretched to cosmic scales. Those fluctuations became the seeds of galaxies. The evidence for this is in the pattern of the cosmic microwave background in the distribution of matter across the universe. Inflation is not certain, but it is well supported. Eternal inflation says, what if inflation never fully stopped? Alan Guth, standing at a blackboard at Cornell University in 1979, had the initial idea for inflation in the middle of the night. He wrote in his notebook, "Spectacular realization." He was 22 minutes into an attempt to solve a different problem, why the universe looks the same in every direction, when the implications of inflation hit him. The mechanism he found not only solved his problem, it implied that inflation, once started, produces more inflating regions faster than any one region can stop inflating. If inflation is eternal, there is no beginning. There is no before because there is no first moment. The universe we inhabit is one bubble, one region where inflation happened to end. Outside our bubble, inflation continues, has always continued, will always continue. The multiverse of eternal inflation is not a poetic idea. It is a direct mathematical consequence of the same equations that describe our universe's first moments. This is the place in the script where I want to be careful about what I say and equally careful about what I do not say. What I do not say is that eternal inflation is wrong. The mathematics is coherent. Guth's work is foundational. The people developing it, Andre Linde, Alexander Vilenkin, are not doing marginal science. What I say is this: eternal inflation cannot, in principle, be tested. The other bubble universes, if they exist, are separated from us by regions of space that are expanding faster than light can cross. No signal can arrive, no observation can confirm or deny. Eternal inflation predicts everything, and a theory that predicts everything predicts nothing testable. This is not a defect of the model, it is a defect of our position in the universe. We cannot get outside it to look. The third answer is the Hartle-Hawking no-boundary proposal. It is the most conceptually strange of the four, and the most elegant. James Hartle and Stephen Hawking published it in 1983. Hawking was already well into the physical decline that would eventually confine him to a wheelchair and a voice synthesizer. He was working on the problem of the wave function of the universe, a quantum description of the entire cosmos, in his office in Cambridge. Hartley was at Santa Barbara. They corresponded and met repeatedly before settling on what became their proposal. The idea is this: at very early times, when the universe was extremely small, time behaved like space. Take a moment with that. We think of time as the dimension in which things change, the direction in which causes produce effects. The no-boundary proposal says that near the beginning, time did not have a beginning. It rounded off, the way the surface of a sphere rounds off. You can travel along the surface of the Earth heading north. You will eventually reach the North Pole. The North Pole is not an edge. It is just a point like any other. There is nothing north of it, not because something stops you, but because north of the North Pole is not a meaningful direction. The no-boundary proposal says that the question, what was before the Big Bang, is like asking, what is north of the North Pole? The question is not unanswerable, it is malformed. There was no moment before the beginning because time itself began. The universe is finite, but has no boundary in time, no edge, no wall, no singularity to approach. The mathematics of this is formidable. It uses Euclidean quantum gravity, a technique that treats time as though it were a spatial dimension for the purposes of calculation, and then converts back. It is not a trick. It is a controlled mathematical move that has a long history in quantum field theory. Where does it break? Here, the no-boundary proposal gives you a universe that starts out small and smooth. Ours does start small and smooth. So far, good. But when you push the calculation to its most precise level, when you try to extract detailed predictions about what kind of universe the proposal actually produces, you find disagreements. Work published in 2018 by Jorma Lucco, Thomas Hertog, and others showed that the most rigorous version of the Hartle-Hawking calculation does not produce a universe like ours. It produces a universe that tends to collapse. Hawking died in March of 2018, a few months after that criticism was published. He spent his last years defending and refining the proposal. The debate is not resolved. There is a problem that runs beneath all three answers so far, and I think it is the most important problem in this entire video. General relativity and quantum mechanics are the two most successful theories in physics. General relativity describes gravity, space-time, the large-scale structure of the universe. Quantum mechanics describes particles, fields, the behavior of matter at small scales. Both are tested to extraordinary precision. Both work. They are mathematically incompatible. When you apply both simultaneously, which you must do near a singularity, where space-time is extremely curved and extremely small, the equations produce infinities. Not large numbers. Infinities. Unphysical results that mean the theory is broken down. This is why the four answers exist. They are four different attempts to solve the problem of quantum gravity, the missing theory that would unite general relativity and quantum mechanics. Loop quantum cosmology is one approach to quantum gravity. The no-boundary proposal is another. Eternal inflation assumes inflation, but does not solve quantum gravity. String gas cosmology is the fourth. Robert Brandenberger at McGill University and Kumrun Vafa at Harvard proposed string gas cosmology in 1989. Vafa was already known for deep work in string theory, the framework in which the fundamental constituents of the universe are not point particles, but one-dimensional vibrating strings. String gas cosmology starts with a simple observation. In string theory, there is a minimum length. Strings cannot be compressed below a certain scale, called the string length. If the universe cannot be compressed below the string length, there is no singularity. The universe reaches the string length and stops contracting. It was never a mathematical point. The model proposes that the universe started in a hot, dense state in which all dimensions were curled up small, the same small size as the string length. String theory predicts that our universe has more than 3 spatial dimensions, possibly 9 or 10. The question it has never answered is, why do we only experience 3? String gas cosmology offers an answer. The 3 dimensions we see expanded. The others remained curled. The mechanism is a balance between strings wound around the compact dimensions and strings vibrating in the large ones. Brandenberger has spent 3 decades refining this. The model makes predictions. Specifically, it predicts a nearly identical spectrum of fluctuations in the cosmic microwave background as inflation does, but with a slight difference in the ratio between 2 types of waves. That ratio might eventually be measurable. Might eventually. In the same condition as loop quantum cosmology, the predictions exist, the instruments do not yet reach them. String gas cosmology also carries the weight of string theory's unverified status. The strings themselves have never been observed. The extra dimensions have never been detected. The model is built on a framework that is internally consistent, but experimentally untested. Four answers, each with a different mechanism, each with a different location for where physics stops being able to speak. Loop quantum cosmology stops at observability. The signature of the bounce may be in the data, in the cosmic microwave background, but we cannot see it yet. Eternal inflation stops at accessibility. The other bubble universes are real in the equations, unreachable in principle. The no-boundary proposal stops at consistency. The most rigorous versions of the calculation may not reproduce our universe. String gas cosmology stops at foundation. The strings themselves have not been confirmed. These are not the same type of failure. They are 4 different ways that the boundary of knowledge looks depending on which direction you approach it from. The physicist Carlo Rovelli, working in Marseille, spending mornings writing philosophy of physics in the same notebooks where he does his equations, has said that the question of what came before the Big Bang may be permanently undecidable. Not temporarily beyond reach. Permanently beyond reach because the information about the pre-singular state, if such a state existed, may not be encoded in anything accessible to us after the Big Bang. The universe may have reset. If that is true, then the 4 answers are not competing descriptions of a single reality. They are 4 internally consistent frameworks, none of which can be selected by any observation we are capable of making. There is a pattern in all 4 answers that I have been thinking about for a long time, and it matters more than any individual model. In every case, the problem is not ignorance in the simple sense. The problem is that we are asking a question about conditions that our best tools, experiment, observation, measurement, cannot reach for physical reasons, not practical ones. Not because we haven't tried, because the information is behind a wall that the structure of physics itself erects. This is a specific kind of not knowing. It is not the not knowing of an unsolved equation. It is not the not knowing of an experiment not yet run. It is the not knowing that comes when a question may be, in principle, inaccessible, when the universe keeps its own records in a format we cannot read. The 4 answers are the 4 smartest things physics has managed to say in the direction of that wall. They do not agree. They do not need to. They are 4 maps of a territory that may never be entered. Georges Lemaître, a Belgian priest and physicist who in 1927 proposed that the universe was expanding 2 years before Edwin Hubble confirmed it observationally, once said that the beginning of the universe was a moment inaccessible to physical science. He said this not to protect theology. He said it as a physicist, looking at what the mathematics could and could not reach. Lemaître was right about the expansion. Whether he was right about the inaccessibility is the open question that all 4 answers are, each in its own way, trying to resolve. Here is where the science stops, not where it becomes uncertain, where it stops. The initial singularity is a mathematical feature of general relativity, not a physical object. What happened at the earliest moments of the universe requires a theory of quantum gravity. There are 4 serious candidates. The predictions of those candidates either exceed our current observational reach or are, in the case of eternal inflation, in principle, untestable. The gap between the 4 answers and a decided answer is not a gap in effort or intelligence. It is a gap in experimental access. The energies involved in the earliest universe exceed anything a particle accelerator can produce by many orders of magnitude. The cosmic microwave background contains only so much information. Gravitational waves may eventually carry signatures of the early universe. The laser interferometer, space antenna planned for the late 2030s, might detect gravitational waves from the first moments, but what those waves could tell us about the question of origins is still being worked out. The map of 4 walls is not a permanent map. It is the map we have now. The mathematics works. The universe is under no obligation to explain why.